Hello, my name is Craig Gallen, and I have been a committer to OpenNMS for over 20 years. In this short presentation, I want to give you an introduction to the OpenNMS project, explain what it does and how it might fit within your organization. So what is OpenNMS? Well, fundamentally, OpenNMS is a network monitoring platform which has been designed to scale to very large enterprises. So first of all, if you've got a large enterprise, if you were a big service provider or ISP, OpenNMS would certainly fit within your organization and be able to monitor hundreds and thousands of data points. So OpenNMS is very scalable, but it's also very extensible. There are many APIs in OpenNMS that allow it to connect to other systems, but also it's possible to use the plugin architecture to write extra features for OpenNMS that you might need for your particular environment. In order to do this, OpenNMS is open source, and it is one of the few open source network monitoring platforms that has been designed for large-scale enterprises. Of course, open source implies that you can do your own support yourself, but there are organizations such as the OpenNMS Group who can provide support for an OpenNMS platform if you need that within your organization. So it is a fully supported open source platform that is designed to monitor very large networks. Now, the open source community is quite active, and you can see from these stats that there are a lot of people contributing to downloading and using OpenNMS, and also feeding back bug reports and new configurations for the platform. It is an active open source community. Now, what about the OpenNMS solution itself? Well, OpenNMS covers most of the aspects of service assurance that you would expect in a large service assurance platform. Many network management solutions only do fault management or only do performance management, and perhaps there would be other platforms to do traffic management in a network. But OpenNMS covers all of these bases. It will do basic event management, fault and alarm management. It will do performance management in terms of collecting data from the network on a regular basis and being able to visualize it. And it will also do network traffic management, where it can gather flow information from the network and actually give you a granular view of how the data is flowing across your network from A to B. It can do network inventory management in that it can discover from devices how they are configured, and it can also do correlation using AI if you wish to use that capability. Now, let me talk a little bit about OpenNMS's architecture. First thing to say is that OpenNMS can be deployed on a single PC and meet the needs of many organizations just as a small deployment of a network management solution. It doesn't need to be deployed in a huge infrastructure in order to work. But this diagram shows you the possibilities for scaling OpenNMS beyond that simple deployment. OpenNMS Core, which we see in the middle of the diagram, is the core OpenNMS system which can run against your network without any extra capabilities. It does need, of course, a database, which is PostgreSQL, in which it stores its configuration data and also stores events and alarms, which it is gathered from the network. But apart from Postgres, OpenNMS will basically work on its own as a monitoring system in a small environment. In a larger environment, OpenNMS can use an enterprise bus to actually communicate with what we call minions, which are remote data collectors that collect data from remote parts of your network. Now, the data bus itself can be Kafka-based, but we can also use ActiveMQ, and we can use Google gRPC as a mechanism for connecting to the minions and gathering data and sending it back to OpenNMS. So all three bus technologies are supported. You can make your choice as to which you wish to use. So the OpenNMS core will make requests to the network to get data from the network, bring it back into the system. And it can do that itself internally, or it can make the request through a minion. Now, the idea of a minion is this is a remote data collector that can either sit on a site behind a firewall or can sit within your cloud infrastructure within a tenancy that OpenNMS cannot directly access. So the minion will proxy for the OpenNMS core, and it will accept SNMP traps, it will accept logs, it will look at flows, and it will also be able to make requests for SNMP gets. All the things that you would expect to do from a core OpenNMS, you could do through a minion if it's connected back to the core OpenNMS. Now, in a very large environment, we may decide that we don't wish to store the data just in OpenNMS core, but we may decide that we actually want to store that data in the data center where it's being collected. And in that case, the minion, instead of collecting the data and sending it straight back to OpenNMS, will send it to another device called a Sentinel, which will store it locally in the data center in Elasticsearch or a time series database. So we've got two methods of deployment here. We can just deploy OpenNMS core and collect the data locally and do whatever management we wish to do with that platform. Or by using an enterprise data bus, we can connect multiple minions which can be remote to the OpenNMS. These minions do a certain amount of scalability for OpenNMS. They make it possible to collect much more data from around the network, but they also give OpenNMS access to remote namespaces in your network, remote network segments, which it couldn't otherwise access. And all of the management traffic goes to the minion, is terminated at the minion, and then is sent back over the bus to the OpenNMS instance, or, as I said, through the Sentinel. Now, let me talk a little bit about how OpenNMS stores data. I already mentioned that OpenNMS uses Postgres. It basically uses that, as I said, for configuration information and for storing alarms and events that it gathers from the network. But over the long term, the desire is not to store alarms in the Postgres database. We want to be able to offload those from the database so that they can be stored for long-term storage. And so we have a plugin for Elasticsearch, which allows us to export alarm change events into Elasticsearch and thereby store very long-term alarm information about your network in a way that can easily be searched within Elasticsearch rather than having to go back to OpenNMS and basically clogging up the OpenNMS database with long-term storage of data. Elasticsearch is also used to store flow data if we use that within the network. And again, it provides a very efficient way of searching those flows to understand what data is going across the network. So that's to do with alarms and to do with flows. Time series data, on the other hand, is data that would be collected by OpenNMS every 5 minutes, say. In which case, the data could either be stored in RRD files, which are flat files that are set up at the initial installation of OpenNMS, and basically the file will never grow beyond a certain size. It's usually set up to carry a year's worth of data, and OpenNMS will store that data in the RRD file, and whenever it reaches the end of the RRD file, it'll go back to the beginning, hence the name round robin database. It's going to store the data in a circular way in that database. Now, RRD files work very effectively for smaller networks, but when you get beyond a certain size, they become unmanageable for various reasons, mostly to do with the number of file handles you actually have to have open in your operating system to support that number of RRD files. So for larger environments, we use other time series databases, Cassandra being one, Cortex being another example, and there are various time series databases we can plug OpenNMS into to store that long-term 5-minute interval type performance data that we're gathering from the network. Now, OpenNMS also has a number of APIs. First of all, there's a REST API that allows us to use Grafana with OpenNMS. That is a very important feature in OpenNMS because Grafana opens up a huge number of possibilities for visualizing the data that was within OpenNMS in an easy way. So you can use the OpenNMS UI to get standard information from the equipment, but if you want to provide customer-specific information then the REST API in OpenNMS can work with the Grafana plugin, which is contributed to Grafana, in order to give you a much richer visualization of the data. Other APIs are available. We can forward alarms and events through the Kafka forwarder, and we can always also forward performance data as it's collected through the Kafka forwarder to other systems. So if you have a data lake of some sort that you want to store that data in, we can forward that out of OpenNMS on the Kafka bus. We can also integrate with trouble ticketing systems, so that alarms in OpenNMS can be related to trouble tickets in your trouble ticket system. And we can use external inventory or CMDB systems to put configurations into OpenNMS. So if you have a CMDB or a large inventory system that can tell OpenNMS about what devices you have in your network, then that can feed in through the REST API to allow OpenNMS to monitor the services that you're expecting it to monitor. So that's a very quick overview of the various components you might find within an OpenNMS system. Now, within OpenNMS itself, it has a strong plugin architecture. OpenNMS itself is based upon something called Apache Carafe, which is an implementation of OSGI. And OSGI is a very well-respected component framework for Java applications. What it allows you to do is to drop plugins into OpenNMS, and they will automatically register with the OpenNMS system in order to in order to provide new features and benefits within the OpenNMS environment. So you can write your own plugins, or there are various plugins that have been written by third parties that can fit into OpenNMS, and will use the OpenNMS integration and API to get access to the underlying system within OpenNMS. Now, the plugins themselves can provide new UI components. They can provide new configurations for monitoring new types of network, and they can provide new ways of integrating. For instance, we have a plugin for Open Daylight that allows us to connect to SDN networks, and other similar plugins are available. So the plugin architecture is a key way in which people can contribute to the OpenNMS project and provide their own plugins to extend the capabilities of the environment. Now let me talk a little bit about the functionality that OpenNMS provides in a service provider context. This diagram is based on the TM Forum Business Process Framework, otherwise known as the ETOM. And OpenNMS would fit primarily at the resource data collection and distribution layer of your environment. But as a system, it can provide information that can be useful in lots of other parts of your organization. So from a problem handling perspective, in other words, fault, we can forward service problem events for managing services. We can provide Grafana reports specifically to customers in order to allow customers to see the state of their segment of the network. And we can provide interfaces to allow customers to get data from your network management system. We can also provide information that might be useful for long-term planning in terms of capturing issues that are going on a repeated basis in your network, around the resources and around the services in your network. Now this diagram basically says the same thing, but instead of thinking about fault, we're now thinking about performance management. And again, OpenNMS collects the data, normalizes it, and makes it available to different layers within your organization in order to be able to provide customer-facing reports, in order to manage services, and in order to be able to manage the underlying resources and to plan for new things that you might need to do to enhance your network. Now, how does it do that? Well, OpenNMS, as I said, is primarily a resource data collection framework. And if we think about a typical network environment now, which we see on the right-hand side, we can see that, typically we have the actual network itself, underlying sets of servers that may be distributed around various data centers. And then over those servers, you'll have virtual machines, or more likely now Kubernetes and containers, which are actually implementing services. and those services are available through URIs which may be exposed to the internet. And then the URIs themselves are being used by applications to actually offer a service to a customer. So starting from the top, going to the bottom, we might think about a customer's service depends on several URIs. For instance, it may depend on Google Maps. It may depend on data being applied to those maps in order to give you a view of a particular service that requires both geographical information and then information laid on top. Now, the reality to offer that service to an end customer is you need several different things to be up and running at the same time. And some of those services may be provided by third parties. Well, it is possible to have minions that are distributed around your environment, perhaps minions on different customers' sites, perhaps minions distributed to your own sites around the organization, which will actually do synthetic transactions at the URI layer and actually understand what the customer experience is going to be through actually doing synthetic transactions the same as these end services would provide. Originally, minions were based upon a technology that was developed for a hospital provider in North America. And in that case, you would have a doctor sitting down in front of patients, and he would want to know that they could get access to the X-rays, or they could get access to the prescription system, or any other number of reports that might be available for the patient records. Now, those systems that the doctor needed to be up all the time, but the doctor would only find that there was a problem if when they actually logged into the system, they found it wasn't working. So the idea of the minion was it could do synthetic transactions in the background all the time, making sure that those systems were up and available. So whenever the doctor actually needed those systems to be available, they could actually see that they were available. And because the minions were distributed around the doctor's surgeries, it was possible to see on a geographical basis that those services were not just available in the data center, but they were available at the point of use. And there could be other things that go wrong, like the network's gone down or DNS isn't working properly, or something's just strange between the doctor and the point at which they're accessing the service, the URI that goes back to your data center. So that was an example of how OpenNMS was designed. It can obviously monitor inside this virtualized infrastructure, because again, you can put minions in here alongside the actual services in the tenancy, and it can monitor the physical infrastructure, and it clearly can monitor the network. So it can give you a view end to end of what's going on in your environment by monitoring different aspects of the service you're offering to your customers. Now, it does that through synthetic transactions, and it supports any number of protocols that can actually get that data. So obviously, it can make basic service requests, pinging devices, ICMP, HTTP, HTTPS. It can also make REST calls using XML or web services, or indeed JSON. It can make calls to DHCP, to DNS, to LDAP, to Radius. It can make calls to all the services that are typically provided by your network to make sure those services are up. It can use JMX to access Java management architecture information. It can contact Windows machines using WMS or WSMan, or it can use WebM to access data. And indeed, it can use the Nagios agents. If you've got Nagios and you're already using that to monitor your network, OpenNMS can actually access those agents running on the machines where Nagios is installed in order to be able to check that the services that Nagios are monitoring are also up. So there's a wide variety of things that you can monitor and you can look at using all of these protocols. You can also discover network inventory. So we can integrate with VMware, for instance, and discover the network from VMware. And we can also discover from the network itself, using SNMP, what the relationships are between devices in your network. So it does data collection on many different layers, and through its distributed architecture with minions, it's possible to place minions around your network and experience what the customer is actually experiencing at the remote part of your network by using the minion to do those synthetic transactions. Now, OpenNMS also does flow collection. So in this case, we're getting more information than you would get from simply polling a port and asking what the bits in and bits out are. In this case, we're using NetFlow, and you can see there are a number of protocols we're supporting that allow us to actually receive data that's coming in from the equipment that's telling us what flows are happening across the network. And that flow information is stored by OpenNMS in Elasticsearch and then made available through the OpenNMS UI and Grafana in order to be able to see what is actually happening in your network from a detailed, granular perspective. So this goes well above the data collection that you would do just to find the bits in and out from a port on a device. This gives you much more detailed view of what's going on in your network in terms of flows. Now, the NetFlow analysis, and this just gives you an example, basically allows you to see that where data is going from A to B across your network, and there's various visualizations you can do within Grafana that allows you to see that data that's being collected by OpenNMS. OpenNMS has a built-in enterprise reporting capability which is based on Jasper reports. You can schedule reports to run against the database, and you can also schedule reports which are generated using Grafana to also be run against the database. The enterprise reporting feature has served very well over the years, but it is beginning to become a bit dated compared to other potential technologies, so it will actually be depreciated in upcoming OpenNMS releases. OpenNMS has a network topology mechanism which is very, very strong. It can discover both layer 3 and layer 2 network connectivity using either OSPF at layer 3, ISIS, CDP, LLDP, bridge, and I'll talk about the other in a minute, but those protocols are all supported through SNMP tables within devices, and OpenNMS can use that information that it discovers to actually work out the topology of a network and work out the relationships between nodes. That can be used in two ways. First of all, our visualization allows us to choose nodes as a focal point and then jump to the next node along. And that way, a user can actually work out that alarms are related through the fact that there's a related node that has an alarm. That's a visualization technique. But also, this can feed into our alarm correlation mechanism, which can allow us again to use the topology of the network along with the alarms in the network to work out what the overall problem is. I said that we supported these protocols for discovering topology, but we also can inject GraphML graphs into OpenNMS so that topology can actually be generated in a number of other ways. A number of the plugins will generate a topology directly, and also we can generate a topology from the inventory database in OpenNMS, whereby we can see a relationship between nodes that are parent nodes and nodes that are underlying those parent nodes. Now finally, I should talk about alarm and event correlation. So out of the box, OpenNMS receives events from a number of different sources. TrapD receives traps, obviously. SysLogD receives syslogs. PolarD is OpenNMS's internal poller, and if it discovers that a service which it is polling is not responding correctly, then it will generate an event. And ThreshD actually generates events whenever it's collecting performance data and the performance crosses a threshold. So between all of these four mechanisms, you can send events into OpenNMS, which EventD puts into a database, but also broadcasts out to the rest of the OpenNMS system. So all of the events in OpenNMS are listened to by all of the other daemons in OpenNMS, and EventD is effectively the event bus that is internal to OpenNMS. Now listening on that event bus is AlarmD, which is a daemon that turns events into alarms. So some events will generate a raising alarm, and some events will correspond to a clearing of an alarm. Now all of this then uses business logic, which is implemented in Drools. Drools is a RETI engine, which basically allows us to create rules to determine how events and alarms are managed within the system. But also, we can use an external correlation engine to correlate inventory information and any other information and then feed back associated alarms. Now, the way this works is that OpenNMS has got a concept of situations where a number of alarms are grouped together. And the external correlation engine can group those alarms together. And we have internally to OpenNMS correlation engines that are based on the graphs of various objects, but also we can use externally AI-based engines such as TensorFlow. So the framework is there, but the actual correlation engine is left up to yourself in order to choose how you're going to do the correlation between these various events. But out of the box, OpenNMS provides business logic in the form of rules to actually correlate events into alarms and do a certain amount of other correlation. Now finally, I should mention business service monitoring, which is a form of event correlation that takes into account the relationship between services. Now you can see in this diagram we have a service graph that relates a number of servers, HTTP servers we can see here, and under these we've got things that are monitoring in the service. So we're monitoring the HTTP service, we're monitoring the node down, and we're monitoring the actual HTTP service itself, so using synthetic transactions. So we're monitoring these servers in multiple different ways, and as a result of these underlying service monitoring activities, we may get an alarm on a server. Now what we can do is then build up a graph of services that say that whenever one of these services is down, well, it itself may have a critical alarm, but from a perspective of the business service, it is an amber alarm because the service is still up, even though it's degraded. You can see there are other parts of the service that may be important. So for instance, the databases may be organized in a cluster. Again, if the databases are, partly down, then, part of the cluster is down, then fine. We know that we've got an issue, but it's not actually affecting the service. But whenever all the databases are down, then that would feed into a major alarm going up into the system to say that there's a business service that's down. So OpenNMS has got quite a sophisticated way in which we can correlate both our service polling and our alarms in our network into service problems, which are then forwarded up to a user to say there is a problem affecting a particular service, and that service has multiple components in it, and as a result of these issues with those components, the service has been infected in a particular way. Okay, so that really finishes this presentation. What I've tried to show you is that OpenNMS is highly scalable, it's highly adaptable, it has the ability to monitor events, traps, and alarms, and it has a number of sophisticated correlation mechanisms to allow you to work out what services are affected by alarms or to work out what alarms are associated with the same situation. It also has the ability to collect performance data and the threshold in that data, generating alarms for a threshold crossing event. And it has the ability to collect more granular performance data in the form of flows, which allow you to say what traffic is actually flowing across your network. And those capabilities together give you a very comprehensive way in which you can do that data collection layer in your network, which will feed up into your higher level operational support systems to enable you to inform your customers that there is an issue. Thank you for listening.